Waiting lines, Supplement B. In this lecture, we'll be talking about analyzing waiting lines. And waiting lines could be a queue of customers waiting to be served. It could also be parts waiting to be manufactured or processed in a factory. A waiting line is one or more customers or things waiting for service. We're going to use customers to refer to the objects in the waiting line. The customer could be a person, or the customer could be a document waiting to be signed. The customer could be a part in a factory waiting to be processed. So we can use the ideas we study and the models we develop in multiple settings, whether that be a service setting or a manufacturing settings. So why do we have waiting lines? Waiting lines are formed when you have demand which is equal to or greater than the capacity of the system to serve that demand. Now, whenever you have this imbalance, you'll see waiting lines. Even if the capacity on average is higher than the demand, so for example, at a particular retail store like Best Buy, let's say the cashiers can process, a cashier can process 10 customers per hour on average. And on average, only 5 customers per hour visit this Best Buy. So you would think that capacity of 10 customers per hour at the checkout process is more than the average 5 customers per hour arriving at Best Buy, so there should never be a queue or a line there. However, there's variability in the system. 5 customers arriving per hour is an average number. In some hours, 12 customers may arrive, right? Because the average being 5 means sometimes you get more than 5, sometimes you make it 0 customers coming in. And also the ability to process 10 customers per hour on average, that's again another average. There could be variability in service times. What if one customer wants to do a time-consuming price match and that customer ends up taking a lot more than 6 minutes of the cashier's time? And so because of this variability in customer arrivals and variability in serving customers, waiting lines can also form when the average demand on the system is less than the average capacity, but at certain time periods you may get more customers or slower processing, and so waiting lines can still form. Why are waiting lines important for operations management? We see waiting lines in a lot of facilities. So you see waiting lines in any place, all service operations, doctors' clinics, retail outlets, other service businesses, like you go to DMV to renew your license. All of them have waiting lines. You go to Disney, go to a resort, you'll see waiting lines. Right? Even in manufacturing operations, you could have waiting lines. Especially think about a job shop where you have, cells or different machines making different products. And depending on the arrivals to this manufacturing facility, you may have waiting lines form in front of certain machines. These videos on this slide, I recommend that you pause the lecture at this stage and watch these videos, because they are a good introduction to some important aspects of waiting line models. Okay. So for example, you learn about why when you're standing in line at a cashier, at a checkout line in the retail store or something like that, or a ticket, you're standing in line to buy a ticket and there are multiple ticket counters. The other lines, more often than not seem to move faster. So why does that happen? You can see how Disney has worked a lot on managing waiting lines. That's crucial to their service. If Disney visitors feel they're always waiting and they're not getting their money's worth, that can affect their business. So they have to do a really good job at managing waiting lines. Okay, and then also why our service systems often run at less than 100% utilization. That has to do with waiting lines as well, because your lines can get too long if you try to have average capacity equals average demand based on the variability in arrivals and so forth. So please watch these videos. They're not really long, and then continue with this lecture. The first thing we're going to talk about is a very high level sort of analysis of a system using Little's law. And there's the good thing about Little's law is that it is applicable. It gives you an approximate result for all sorts of situations. So you can apply it to get a sense without having to accurately model how your arrivals happen, how you serve them, and so forth. Little's law states that the average number of customers in a stable system is equal to the average arrival rate, lambda. So this Greek symbol here is called lambda, multiplied by the average time a customer spends in the system, W. So it's L equals lambda multiplied by W. Okay, so example will make this more clear. Imagine 20 customers arrive at a taco food truck per hour. So that means lambda equals 20 customers per hour. They stick around for 0.5 hours or 30 minutes. So the time that a customer spends in a system is 30 minutes or 0.5. And so what would be the number of customers around this food truck? So we'll do L equals lambda times W. So L equals 20 times 0.5 or 10. So on average, we expect to have 10 customers around the truck. This could be useful information so that we park the truck in an area where 10 people can gather and so forth, right? And so this can give you an approximate answer. We'll do more detailed analysis, as we go through the lecture as well. Let's do another example. Imagine a motor vehicles service center. There's a manager there, and they want to get a quick idea of the time customers spend in the DMV facility to renew their driving license. Now, for this manager, it is costly and time consuming to gather data on time spent by individual customers, which would be useful, but they want to get a quick idea of the time the customers spend without having to do any data collection. So they can use Little's law. Okay? The manager occasionally can scan the facility and count number of customers in it. So it's fairly easy if you are in the facility to estimate L. L is the number of people in the system, right? Because you can just do a count a few times a day or once or twice a day, right? And then you can just average it out to get an average value of L. And the manager's assistant can monitor people arriving per hour and finds that about 40 people arrive per hour. Again, this is kind of quick data gathering. You can just stand around the door and kind of count how many people walk in per hour. You do it for a few hours, get an average. So based on these two numbers, you can estimate how long it takes people to renew their license, W. If L equals lambda times W, then W equals L over lambda. And because there are 30 people present and about 40 arrive per hour, then each customer spends about 0.75 hours in the DMV facility or 45 minutes. So using very little data without having to go into assumptions about arrivals or any probabilities, we're able to kind of get a rough estimate of the time people spend in this facility. So that is why Little's law is very useful. Let's do another example. At a manufacturing process, 5 pieces arrive per hour. Okay? And it takes 3 hours to work on each piece to produce the final product. Okay? So we need to figure out for this workstation, which takes 3 hours to work on each piece to make the final product, and 5 pieces arrive per hour, how much inventory, work in process inventory, would be at this workstation. That can be a useful metric to know, because then we can design storage around that workstation to hold those work in process inventory safely. And so we can use Little's law. L would be the number of things in the system at this workstation, and that is equal to the arrival rate, 5 pieces per hour, times how much time a piece spends at this workstation, which is 3 hours. So 5 pieces per hour arriving times each spend 3 hours there. That means we'll have 15 piece work in process pieces at that workstation. Okay. So this allows us to determine how much physical space is needed at this processing stage. Little's law is extremely powerful and simple, and so it is something that each manager should have in their toolkit. You can use it if you manage any sort of service operations to get quick estimates of how long people spend in a facility, or how many people are there going to be in a facility on average, and that can help you manage the facility better. Yeah. Now, Little's law gives us a big picture view of things. It doesn't give us a lot of different statistics. It only gives us average number of people in the system, average waiting time. It doesn't tell us what the queue length, how much time they spend waiting in the queue versus how much time they spend getting served, for example, which can be important because when people are waiting to be served, they are more impatient. Once they start getting served, like let's say at a doctor's clinic, you're going to be impatient to see the doctor, but once the doctor arrives to talk to you, you may not be as impatient than dealing with the doctor. You may not bother you, for example, right? So Little's law is just an overall picture. We can do more detailed analysis. We can look at utilization of the system, how long people spend waiting, how long people spend getting processed or getting the service, things like that. And for that, we use models which are called queuing theory or waiting line models. Okay. These models can give us more detailed insight into the likelihood of various scenarios. We can also use these to figure out, how much space to have, how much the queue can be, the maximum queue can grow, so we know how much worst, in the worst case, how much space we need for the queue, things like that. Waiting line models can get complicated for complex scenarios where customers go through multiple stations and multiple stages of processing. And so for those scenarios, we have to resort to simulations to answer questions about the system, about how much queues you'll have in different stages and so forth. In this lecture, we're not going to talk about simulation, but I want you to know that if you are faced with a situation where the assumptions of the waiting line models don't hold and you can't apply the analysis we learned today, then what do you do in that situation? Then you go to simulations. So we're going to define some basic elements of a queuing system, and then we're going to analyze queuing systems which have those elements. If these elements can capture many real-life situations very accurately, if you are faced with a situation where this model that we are presenting in the lecture does not hold, then obviously you can use simulations instead of the waiting line models we discuss. So we have the customer population, that is the population from which the customers arrive. Then we have the system itself, how many servers there are in the system, also called channels, how many stages, whether it's a single line or multiple line, or it's the priority rule. And the probability distributions of arrivals, how many people arrive in a given time period, and the probability distribution of the service time, how long it takes to serve a customer, because service times will vary from customer to customer. And so we model them as having an average service time, but then the service time can vary around the average. It could be less or more. So let's look at these elements. Customer population is the source of input to the system. So if this yellow box here represents our system, then the population is the possible units or customers that can enter our system. So if you are a service business in Grand Blanc or Flint, traditionally you only see customers from Flint, then your population would be the people in Flint, because some of those people could come to your business, for example. The only thing we're interested in here is how big is the population, okay? Because it simplifies our analysis, and most of our models assume that this population is much bigger than the people within your shop or your business. Imagine a grocery store in Flint. And imagine that, in the grocery store, usually you find anywhere between, 1 to 10 people in the store. If this grocery store was in a very small town in the middle of nowhere where there was a total of 10 people in the town, once you had 10 people in the grocery store, the probability of anybody else coming to the store would be zero, because the whole town, or close to zero, because the whole town is basically inside the store. And so when you have a very small population, as more and more people come to get service from you, the probability that additional people will arrive at your store decreases drastically, right? And then that complicates the analysis. And that's called a finite population model. So we're not going to talk about those today. We're going to talk about situations where the population is much bigger than the people that your system can usually serves. So if our store usually serves 1 to 10 people, if the population of that town or city is 50 or 100 or thousands, then that's much larger than 10. And so even if we have 10 people in the store, that doesn't change the probability of how many people can arrive in the next few minutes or the next hour. And so that is the type of systems we will analyze, and that is the most common situation. Most businesses, the number of people inside the business is much smaller than the potential number of people who could visit that business theoretically, because surrounding that business there are a lot more people who live there, or in the service area of that business a lot more people live there. So this is really, I'm just telling you this so that you understand the difference between a finite population. When we say one of the assumptions of our analysis is an infinite population, all we mean is that the population is much larger than the people inside the system. Now, there are some rare scenarios where you do want to use finite population models. Usually we see them in maintenance scenarios. So let's say you're a worker which maintains photocopiers or printers in an office building. Okay, so you're an IT repair person, something like that. And in that office building, there are, let's say, 10 printers. So the population of printers that can potentially visit your repair center in this office building is 10, right? Because you can get called to serve or service or repair one of these 10 printers. Now, if you already have got service calls for 5 of the printers out of 10, the probability that you'll get another service call is kind of low, because already half the printers are, in queue to be served or maintained. Similarly, if you get 6, 7, 8 requests, then the probability of getting an additional request decreases, because there's very few printers left in the building to be potentially be served. So in some sort of maintenance scenarios, when you only have a few pieces of equipment and you're looking at, okay, how many pieces are queued up for maintenance, you may have to assume a finite population, because you're only serving equipment within one building. Okay, but in most scenarios, infinite population assumption is correct. Infinite doesn't mean theoretically infinite, just means this number is much larger. The number of people who can visit your store or your operation is much larger than the people who are inside the operation or the facility. Okay, so what are channels and phases? Channels is the number of parallel servers for servicing customers. So if you look at the first picture here, where you have a service facility, a green box, that's single channel operation, because all the customers that arrive, they have to go to this one workstation or service desk. Okay? Option C, with 2 service facilities in yellow and green, represents a multi-channel operation, where customers who arrive, they can go to channel 1 to be served by this station 1, or they could go to channel 2 and be served by station 2. Often you see, if you've ever been to Social Security office, they'll have multiple windows, and you sit down, you have a number which is your queue number in the system, and then you have multiple channels because there are multiple windows where you can go to get served. If some stores would have the same thing, you enter a queue, like self-checkout stations in a lot of stores like Walmart, Kroger, you enter into a queue, and then there are multiple self-checkout counters, and so those would be the multiple channels. Okay. Phases are when you go through multiple stages of processing. So let's say you go to a hospital and first the emergency doctor sees you, that's phase 1, and then they send you to do an x-ray, that's phase 2, and then after the x-ray you get admitted into a ward in the hospital, and then that's like phase 3. So you get service at multiple stations and you go from one station to the other. That's shown in the picture B here on this slide, where you go to phase 1, workstation 1, and then after you're done at that part you have to go to phase 2, workstation 2, to finish up your processing. And then you can have a multiple channel, multiple phase, which is the diagram D, where you have more than one server for phase 1. So when you enter the system, you go to one of the 2 workstations. Once you finish phase 1 of processing, you have another multiple server channels or servers where you can pick one from for your phase 2 processing. So think about it, you go to a hospital, there are multiple doctors who could see you in the emergency department. So one of the doctors sees you and then they send you off to get an x-ray. Again, there are multiple x-ray rooms, and then whichever x-ray room is available, you go there. Right, so it'll be a multi-channel, multi-phase system. Okay. We will analyze situation A, single channel, single phase, and situation C, multi-channel, single phase. We will not be analyzing multi-phase systems today, just to keep things manageable for this course. Also for multi-phase systems, it's very quickly you start running into having to use simulations, because what complicates things in multi-phase systems is that for phase 2, if phase 1 is kind of processing some customers, phase 2, how many customers arrive at phase 2 kind of depends on how many customers phase 1 can process. So if phase 1 has a slowdown or blockage or something, phase 2 might sit idle just waiting for people because they're all stuck at kind of phase 1. So there's a dependency introduced in the system, where subsequent phases depend on the phase prior to that to send them customers, and that introduces complexity in the analysis. And so often we use simulations to handle multi-phase scenarios. Since we're not doing simulations today, we are going to handle only A and C, which we can handle with relatively simple formulas. Now if you look at picture C here, where you have multiple channels, also called multiple servers because each channel is like a server, you have 2 options. One is you could have one line which feeds into all the channels. This is the picture on the left on the slide, picture A. You probably have seen this sort of system in several places, like airports. You go to the security line, there's one long snaking queue, and then you may have 2 or 3 security lines where you go through the x-ray machine, and those will be the service facility or servers or channels, and at the end of the queue you go to whichever one is open or available. The other option you might have seen at some checkout, at Walmart checkout or Kroger checkout, not the self-checkout, the other regular checkout, where you have multiple servers. These are all the checkout counters, and then in front of each counter you can queue up, so there's multiple lines. Okay, so this multiple lines, each line with a single server, you can analyze this as picture A here, single channel, single phase, because each server has its own queue. So if you look at this red box I've drawn around it, this is a system which is just a single channel system, and you have 5 single channel systems. So you just analyze the 5 single channel systems individually. Whereas the picture on the left, which is picture A, diagram A here, you can analyze the whole diagram as one system because one queue feeds all of the channels or the servers that are available in this system. We'll do an example of this towards the end of the lecture, so it will make more sense then. Then you could have a very complicated system where you have different types of customers that queue at different facilities, and then from different facilities they could go to different other facilities. So you have many channels and many phases. A good example would be something like a hospital with many departments, like a very large hospital which does treatments for many different things. And then you have people coming in, so people coming in with eye problems, they go to the ophthalmology department, and then they may have different testing labs or other facilities for ophthalmology, and other people may go to get an ultrasound or x-ray or MRI scan and go to other facilities. Some people may go for surgery, they may need anesthesia facilities. So different customers not only go to different workstations or servers, but they also go through different phases, because the person going through surgery may go through anesthesia and x-rays but may not go through some other sort of testing, whereas a person going for some other problem may go through different phases. So that can be very complicated to see how much queues can form and analyze the whole system. To do it mathematically, so often we'll use simulation for that. Sometimes we can simplify the analysis to think about a Disney theme park. Once you have passed the initial queue to get into the theme park, now you can go to any ride, and then we can treat each ride independently, because usually in theme parks you don't have rules that you have to do ride X before you can do ride Y, and if you've done ride Y and Z, you can only then do ride F or something like that. There's no rules like that. Each ride is independent. You can just go to that ride, queue up in front of that ride, and be served by that ride. So you basically have a whole bunch of single server, single phase, this sorts of systems located throughout the park, and you can analyze each system independently, just a single server, single phase system. Right. But if you do have dependence between them, like in a hospital, then you would have to use simulation to analyze them. Then before we analyze the system, we have to look at priority rules. So the simplest rule is first in, first out, or first come, first served. So FCFS or FIFO. And that is that whoever arrives first has priority, will be served first, i.e. you move through the line in the order you arrived. So if you are at the back of the line, you have to go through the line before you can be served. There are other rules, which is earliest promised date, EPD rule, to prioritize tasks which are about to be late. Sometimes you see EPD at the airport when you are standing in the line for security, and they say whoever is flying by Delta flight 912 or whatever to Hawaii, the flight is leaving in 20 minutes, you have to come out of the line and we will serve you first. So we will prioritize you, right? And so they do FIFO at the airport, but sometimes they will skip FIFO and do EPD, where customers whose time, instead of date, there's time in this case, whose promised time, the time the flight has to leave, is very close at hand, and so they need to be prioritized. And then shorter processing SPT is sometimes used to reduce congestion, where you say, okay, we have a huge congestion in our factory or our facility, so we just want to get some customers or some product out of the facility to reduce congestion. So the best way to reduce congestion in the facility is to quickly process those items or those things or customers which need very little amount of processing. So we're going to quickly process them and get them out of here, and that will reduce congestion. Right. Sometimes you see that with express checkout lines, which if you have bought 10 or fewer items or 8 or fewer items, you go to an express checkout line, and that is you have a shorter processing time, so they don't want you to wait in a long line behind people with carts full of stuff because you only bought 3 items, right? Now we do have, in real life, we have variability in these systems, and so we have to model that variability to be analyzed these systems. So there's 2 sources of variation we're going to model, okay? One is that customers arrive not as clockwork. So if you have a system where you expect, 10 customers to arrive per hour, you're not going to get these customers arriving 10 minutes apart. You're not going to get a customer at time 0, then 10 minutes, then 20 minutes, then 30 minutes, then 40 minutes, like that. They're going to arrive at random times, and you may have 3 of them arrive together, and then nobody arrives for the next 20 minutes. So there's variability in customer arrivals. That's the first source of variability. The second source of variability is that different customers require different amounts of service time. So somebody buys 10 items from Walmart, somebody buys 50 items from Walmart, right? So they take different amount of time to check out. And so you have service time variability. The most common way we model the variability is we say, okay, the arrivals have a Poisson distribution. So the number of people arriving for a given amount of time is random and has a Poisson distribution. And for service times, we say, okay, there's an average service time, but service times are exponentially distributed. So some people take a lot more than the average time. Some people take less than the average time. And so we have an exponential distribution to capture service times. Okay, if you notice that Poisson and exponential distributions are related, actually it's negative. If you want to be, to be precise, the distribution for service times is negative exponential distribution, because as you increase the amount of time taken, the probability that you take more and more time for a customer decreases, because you get very few customers that take 5 times the average time, for example. Right? So if the average checkout time is 10 minutes at Walmart, it's rare you'll get a customer that needs 40 minutes to check out, right? It's very rare, because the more you move away from the average, the lower the probability that happens. So negative exponential distribution is related to Poisson, because if service times are exponentially distributed, that means the number of people you serve per unit time is going to have a Poisson distribution. So whenever we have count data, how many people arrive, how many people were served, Poisson is a good distribution that we use. It doesn't mean that every real life situation, the numbers are going to be Poisson distributed. For simplicity, we're going to assume Poisson and it's approximately correct in many situations, and we're going to be fine. If you want to be, a lot more accurate in real life, you can actually measure data and see which distribution fits the data best, and then do a simulation for whatever distribution fits your data best and get your results based on simulation. So this is just an example to show you the relationship between Poisson and the negative exponential distribution. So number of customers arriving in a unit of time, e.g. 1 hour, has a Poisson distribution with a parameter called lambda, which is the average arrival rate. So on average, 20 customers arrive per hour. That's lambda. And if you look at this histogram, this picture here, you can see that, there's a high probability that whatever is the average happens for Poisson distribution, but you can also have more than the average happen, and the probability decreases as you move far away from the average. Now, the time between customers arriving, if the number of customers that arrive per unit time has a Poisson distribution, then the time that elapses between a customer arriving and the next customer arriving, that time will have a negative exponential distribution, because these two distributions are related. Okay. So in any way, if this is a little bit complicated, don't worry. All you need to know is that all of the models we study today, they're going to assume that the arrivals are Poisson distributed, and the service times have a negative exponential distribution. Sometimes you do have fixed service times. Let's say you go for a car wash and then the car just moves on a conveyor through the car wash. It takes the same amount of time. And we do consider that situation towards the end of the lecture, where we say the service time to serve a customer is fixed. It's not random. It doesn't have an exponential distribution. It's just always 10 minutes. It's always 5 minutes, right? So we do that situation as well. So how do you estimate what is lambda? How many customers arrive per hour? So you can measure how many record the arrival times for customers. If you have video recording in a store or in your center, you can just look at the timestamp from the video, just record it, okay, based by analyzing the video when customers arrive. You can have sensor in the door, which record whenever customer walks in from the door. And if you have different entrance doors and different exit doors, that's easy to do. Even if you have the same door for entry and exit, if you have 2 doors or you put 2 sensors, which sensor gets triggered first can tell you if the people are moving into the store or moving out of the store. So you can still get this data, all right? And worst case, you can just manually record the data, just stand there and record the times customers arrive. So day 1, we can see that between 8 and 9 a.m., 3 customers arrived at different times. So once you have data like that, you can calculate the average arrivals per day or per hour. So you can then record in Excel, okay, 3 customers arrive in the first hour, 3 in the second hour, 3 in the fourth hour, 2 in the fifth hour, so on. And then you can take an average of that column if you want arrivals per hour. If you want the arrival rate per day, you can just sum the number of customers that arrived per day on day 1, day 2, day 3, and take the average, right? Same thing we can do to estimate the service rate, how many customers we serve per unit time. So we can record the service times, how long it took to serve each customer on day 1, day 2, day 3. For example, in the middle picture, we can see on day two here, the second customer, they took this much time. Based on the y-axis, that took this much time to be served. Right? Then we can record all these times in Excel and take an average and find the average time a customer takes. So let's say we find that the average time is 5. On average, a customer takes 5 minutes to be served. Then mu, the service rate, and the number of customers served per hour, can be estimated as 60 minutes divided by 5 minutes on average. That will give us 12 customers per hour can be served on an average served by our system or our server, because we'll do this for each server, right? If you want to do the customer served per hour, then we can just take 1 divided by average service time in hours. So let's say we find out that on average a customer is served in 0.2 hours, then 1 divided by 0.2 will give us the service rate, or the number of customers per hour that we serve. Once we have seen how to get data on customer arrival times and use that to calculate arrivals per hour or per day, and we have looked at how to measure the service times and use that to get the average service time and then find the customers served per hour, we can then proceed to do further analysis. These two are sometimes called fundamental parameters that we use in our analysis. So arrival rate is lambda. Often it's expressed in per minute or per hour. In some situations, you may even have arrivals per second. So imagine a Netflix server sitting in Ireland, and it gets requests to stream different movies and TV shows, and it may get thousands of requests per second. So depending on the context we are working in, we can pick the time units we want to work with. So, in operations, we are often working in arrivals per minute or arrivals per hour, but in other domains, we are also working in arrivals per second. Same thing for the service rate, which is how many customers are served per unit time. So we need the average time it takes to serve a customer, and then we divide that by 60 if it's in minutes to get the number of customers served per hour. If you want to get the number of customers served per minute, then we take 1 over the average service time in minutes. Let's look at the Poisson probability distribution. The Poisson probability distribution can give us probabilities of n customers that arriving in a unit time t. So by this formula here, so the probability that n customers will arrive in time t is given by you multiply lambda by t raised to power n divided by n factorial multiplied by e to the power of minus lambda t. Now, if you're not familiar with the exclamation mark, this means factorial. You can Google how to calculate the factorial of a number. It's relatively straightforward. The factorial of a number is the number multiplied by a subsequent smaller integer. So factorial of 5 is 5 times 4 times 3 times 2 times 1. Factorial of 3 is 3 times 2 times 1. Factorial of 1 is defined as 1. E is the constant 2.71828. You can find E using the exp function in Excel. And so it's equals exp in brackets 1, and it'll give you the value of E in Excel. And you can also do use the exp function to compute this term in Excel. Let's do an example. So let's say we have 4 customers arriving per hour on average. So that's lambda is 4 customers per hour. They come to this pizza shop, and we want to figure out what is the probability that we'll get 10 customers in 1 hour. So t is 1 hour. The time units of t and lambda have to match. If lambda is 4 customers per hour, you can't have t in minutes. You can't say t is 60 minutes or 100 minutes. You have to have it in hours because lambda is customers per hour. If lambda was customers per minute, then T would have to be in minutes. So units would have to match up. N is 10. We want to find the probability that 10 customers arrive at this facility. So we'll just plug into this formula that we got from this slide for the Poisson distribution. Lambda will plug in 4. T is 1, N is 10, E has the value we already saw, and when we solve this expression, we get 0.0053. That's a really small probability, less than 1%, because 0.01 is 1%. This is 0.005, even smaller, that 10 customers will arrive in an hour. Okay, so if we are worried about having space for 10 customers, we don't need to worry too much, because given an average of 4 arrivals per hour and our Poisson distribution, we don't really expect to have 10 customers arrive within the same hour at our pizza shop. Now let's look at service times. Service times have a negative exponential distribution where the probability that it takes less than some threshold capital T, the time to serve a customer takes less than this less than capital T time, is given by 1 minus E. Again, E is the same constant we looked at here, 2.718. 1 minus E raised to the power minus mu times T. Mu is the service rate, how many customers you can serve per hour, for example, and T is the time with the same units as mu. Okay, let's look at an example. So let's say we are able to serve 3 customers per hour, which means on average we spend 20 minutes to serve a customer. So that's why we can serve 3 customers per hour, right? So if we serve 3 customers per hour, what is the probability that we can serve a customer in 10 minutes or less? Now we have to convert 10 minutes to hours because mu is 3 customers per hour and the time units need to match. So here we'll divide 10 by 60 to get 0.167 hours, and then we can plug into our formula. Probability that the time taken to serve a customer is less than or equal to 0.167 hours is simply 1 minus e to the power minus mu times t. That'll be 1 minus e to the power minus 3 because mu is 3 times 0.167. This evaluates 2.394. So there's almost a 39% chance, 39.4% chance that we can serve a customer in less than 10 minutes. Now, how do you compute this quantity e to the minus 3 times 0.167? You can use the exp function in Excel. So you do equals exp, and then in brackets, you pass in the expression that you want to raise the e to the power of. So we're raising e to the power of minus 3 times 0.167. So we pass that into the exp function, and we get 0.6059, the value that it evaluates to. And so these examples here, these 2 examples, they were the purpose here is to show you how you can use the probability distribution to answer questions about how likely it is to get this many customers arriving, or how likely it is to spend this much time on a particular customer serving them, right? And so we don't often need to do these sorts of calculations because we can just use the waiting line formulas that we're going to discuss next to compute various statistics about the system, but it is useful to know what probability distribution we're using to model the system. Now, when we model the waiting line systems, we're going to use Kendall notation to specify what type of system it is. Kendall notation gives us 3 pieces of information. It has 2 letters, a letter followed by a forward slash followed by a letter, forward slash followed by K. The 3rd letter is the easiest to interpret. K is a number which tells you the number of servers or channels you have in the system. And the first 2 letters tell us about the probability distributions. So the letter in the first place, placeholder A, that tells us the distribution of customer arrivals. That's always going to be M for us because M is used to represent Poisson distribution for arrivals. The letter in the second place represents the distribution of service times, or the number of customers we serve per unit time. We're also going to use M in the second place because we are, for the most part, going to assume negative exponential distribution of service times. However, we will do one case where the second letter will be D, which means deterministic or a fixed service time. So the system will be MMK MM1, MMK, MD1, like that. And so you'll see these Kendall notation being used. So this slide is just to explain to you what this means. This is important to know because if you go out and read books on queuing theory or waiting line models, or you watch YouTube videos, or you try to get more knowledge on this topic, this notation will often pop up. So I just want to give you a heads up. The first two letters tell you about the probability distributions of arrivals and service times, and the last letter tells you about the number of servers or channels in the system. So let's look at a single channel server system, MM1. This system, we already saw a picture of that. So let me show you this here, picture A, where you have a single server and there's a queue in front of it. That is an MM1 system. So for an MM1 system, we have, if we know two parameters, a lambda, which is the average arrivals per time period, and mu, the average number of customers served per time period, we can compute various characteristics of the system, which are listed on this slide. We have like 1, 2, 3, 4, 5, 6, 7, 8 formulas. The first formula is the probability that there are no units in the system, that the system is idle. Okay, that's called P0. 0 represents 0 people in the system, and that is given by 1 minus lambda over mu. So very simple calculation. The utilization of the system is called rho. This letter, this tilted P, is called rho. It's a Greek letter. The utilization of the system is simply lambda over mu. Okay. So just these simple calculations can tell us the utilization for our servers, can tell us the idle time or idle percentage for our server, the probability that the server is idle. We can also find the probability that there are n units in the system. When we say in the system, we mean the queue, or they're being served by the server or the channel. So it could be either in the queue or the channel. So the number of units in the system is given by P of n, which is simply lambda divided by mu raised to power n multiplied by P0, which is right here. We can also represent the same thing in terms of utilization. Rho is utilization raised to power n multiplied by 1 minus the utilization. The average number of units in the waiting line, this is a really important statistic. It tells us the length of the waiting line. So what is the expected length of the waiting line for this system when you have lambda service rate and lambda arrival rate and mu as the service rate? That LQ is given by lambda squared divided by mu times mu minus lambda. The average number of units in the system, L, is simply the number of units in the queue plus the number of units being processed on average at any given time. And so L, the number of units in the system, equals LQ plus lambda over mu. Now remember that Little's law also had L, the number of people in a system. Little's law does not assume a Poisson distribution for arrivals, does not assume an exponential distribution for service time. It just gives you an estimate overall without making any of these assumptions. But these formulas that you see here are going to be more accurate than Little's law. However, these formulas can only be used when certain assumptions are satisfied, which we'll talk about later in the lecture. So if we can use these formulas, we tend to use these formulas more. Now, in terms of homework or exam, the question will clearly specify whether the question wants you to use the Little's law or not. If the question does not ask you to use the Little's law, then you will be using something here. Also, you can tell from the data given. So in Little's law system, you will not be given the service time, right, the average service time or the service rate, and so you wouldn't be able to compute mu, so you wouldn't be able to use these formulas anyway, so you'll know it's a Little's law type of problem. We can also find the average time a customer waits, WQ in the queue, that's given by LQ over lambda, and then the average time a unit spent in the system, that's the time spent waiting, WQ plus 1 over mu. This is the time spent being processed. So you wait, and then you get processed or you get served, and that is the total time W. The probability that an arriving unit has to wait for service is given by PW, probability of having to wait. That's lambda over mu. Notice the probability of having to wait is equal to the utilization. So if the utilization is 70%, there's a 70% chance when you go there, you'll have to wait for to wait to be served, and if the utilization is 70%, there's a 30% chance that you won't have to wait to be served. There'll be no queue. You just you'll not have to go into a queue. So that's an MM1 system. It's a simple system. There's just one queue, one server. Okay, and both the arrival rate, the number of arrivals per unit time is Poisson. The number of people served per unit time is Poisson, which means the service times are exponentially distributed. Saying that service times are exponentially distributed and saying that the number of people served per time period is Poisson is the same thing, because the exponential and Poisson distributions are related. So that's what the two M's mean, and the one means we have one server. Now, what happens if we have a deterministic service time, like a car wash? Everything is automated. You come in and every customer spends the same exact amount in the system. That means that the service time is no longer random. It's no longer has an exponential distribution. It's just a fixed number, right? And so that we call that the deterministic or constant service time situation. Most of the formulas are the same as an MM1 system, right? You'll notice that the formula for LQ, the number of people waiting in line, changes a little bit. So it's lambda squared by 2 times mu times lambda. This can also be written in this way. Why am I writing it in this way? Because a lot of times people will compute the ratio lambda over mu, because notice the ratio lambda over mu shows up in many places. So oftentimes students will compute the ratio lambda over mu and store it in some place. And then if you've already stored the ratio lambda over mu, you can quickly calculate LQ by taking that ratio, squaring it, and divide by 2 times 1 minus that ratio. But you can also compute it this way. They both are exactly algebraically equivalent expressions to give you the length of the queue. So the length of the queue, LQ, differs from MM1 system. You'll notice that there's the LQ, the length for an MM1 system, is going to be more than the LQ, the length for an equivalent MD1 system. Why? Because you have no variability in service time. So in an MM1 system, if it takes longer to process a customer, like in Kroger, the person ahead of you has a huge cart full of stuff, they're going to take a long time. That's going to increase the number of people in the queue, because you're going to spend more time in the queue. But in a deterministic system where every customer takes exactly the same amount of time, then the queue is going to be shorter than an equivalent MM1 system. So the LQ formula is different. And then all these quantities which depend on LQ, because L depends on LQ, WQ depends on LQ, W depends on WQ, which depends on LQ. All of these three quantities here are also going to have a different value than an MM1 system, because the LQ value is different for MD1 system than an MM1 system. Yeah. Otherwise, they're both very simple. If you look at these two slides, you print them out, put them side by side, very similar formulas. The only thing is that the waiting time and the waiting queue length is a little bit shorter for an MD1 system, because there's no variability in the service time. Okay, so let's do an example. Let's say we have a food cart at a fair. Maybe we sell hot dogs or French fries, something like that. And about 0.75 customers arrive per minute at a food cart to place an order. And we serve one customer per minute on average. So it takes us 1 minute to serve a customer. So our service rate is 1 customer per minute. What are the characteristics of this system? It's an MM1 system. There's just one server, just one cart, and we have one queue in front of the cart. Okay, and we'll also find the probability that there are 3 units in the system where we have n equals 3. So first of all, what is the probability there are no units in the system? 1 minus lambda over mu. Lambda is 0.75. That's the arrival rate. Mu is 1, which is the service rate, how many customers we serve per minute. And our probability that there's no units at all at the cart, at this food cart, is 0.25. So 25% of the time at this food cart, you're going to have nobody there. Right? The utilization of the food cart is just going to be 1 minus the idle time. So it's going to be 1 minus 0.25 or 0.75. Or you can calculate directly as lambda over mu. So 75% of the time we are being utilized. We are having to serve customers and doing stuff at the food court. What is the probability that we have n people, n equals 3? We have 3 people at the food court. That is the probability Pn, which is given by this formula, lambda over mu raised to power n, which is 3 times P0. P0 is 0.25, already computed up here. When we compute that, we get a probability of 0.105, or about 10.5% of the time we'll have 3 people at the food court. What is the average length of the waiting line? That is about 2.25 customers. On average, this many customers are waiting in front of the food court. This does not include the customer being served. So if you have one customer being served, in addition to the customer being served, your waiting line is 2.25 customers long. How many systems do we have in the system on average? That's going to be LQ plus lambda over mu, which is 2.25 plus 0.75 divided by 1, which is 3. So on average, we have 3 customers in the system. What is the average time a customer spends waiting to be served at the food court? That's WQ given by LQ over lambda, which is 3 minutes. What is the average time a customer spends in the whole system? That includes waiting time plus time to be served with their hot dog. That is going to be WQ plus 1 over mu, which is 4 minutes. The probability that an arriving unit has to wait for service, PW, is simply 0.75. So 75% of the customers who come to the food court have to wait some amount of time before they are served. But 25% of the customers, when they arrive at the food court, there's nobody there and they get served immediately. So all of these statistics that we have computed about this system, about the simple food court system, they can help us manage things better. You can ask what if questions. What if on a particular day it's very busy, there's lots of customers, and the arrival rate becomes 0.9 customers per minute instead of 0.75 customers per minute, right? What happens then? How long do the lines grow? You can do all this calculation again and compute how big the line will be, how big the wait time will be, and so on and so forth. And then you might say, okay, well, my lines are getting too long. I need to increase my service rate, i.e. decrease my service time. So I need to serve a customer in 30 seconds. So then I can serve 2 customers per minute. And then you can decide that, and you can invest in your process or technology to be able to handle that, right? So you can do all of that analysis based on these formulas. Now, I highly recommend that you put these formulas into Excel. So this is a picture of an Excel sheet, a sample Excel sheet, where you can put in the arrival rate and the service rate, and you can put in the formulas, all the formulas you see here. In this slide, you can put in these formulas into Excel, where you refer to cell B7 and B8, which has lambda and mu, and you calculate everything based on lambda and mu, and you build this Excel template. What this allows you to do is whenever you have an MM1 problem in the homework or the exam, you open your Excel file, you put in the value of lambda, you put in the value of mu, and ta-da, Excel calculates all of these things for you. Right, and so you can make your Excel template to compute all of these characteristics of an MM1 system. Let's do an example of an MD1 system. So Surf Bubbles is a car wash which has a single car wash lane. So that's why they have just one server. And customers' arrivals are random with an arrival rate of 21 customers per hour. That's going to be lambda, the arrival rate. And service time is fixed to 2 minutes per customer. So it takes 2 minutes for a car to go through the car wash, and it's the same time. It doesn't vary. Calculate the waiting line characteristics for this system. Because the service time is 2 minutes per customer, we can convert that into a service rate. So service rate mu is going to be 1 divided by 2 minutes per customer, or 0.5 customers per minute. And if mu is in minutes, we can also convert lambda from 21 customers per hour into 21 divided by 60 equals 0.35 customers per minute. If you prefer to work in hours, you can do that. Some people don't like to have fractional values like 0.35 customers per minute, 0.5 customers per minute. They feel more comfortable working with larger numbers in per hour. So then you can keep lambda to be 21 customers per hour, and then you can convert the 2 minutes per customers into a service rate per hour. If you spend 2 minutes per customers, how many customers will you handle in 1 hour? That will be 60 divided by 2. That will be 30 customers per hour. So you can work with lambda equals 21 and mu equals 30. You get exactly the same answers that I got here. You'll be working in per hour terms. Your WQ will be like 0.01, whatever. It'll be some fraction of an hour. When you convert it to minutes, you'll get 2.33 minutes, right? And so the WQ and W will be different because they'll be in hours, but when you multiply that number by 60 to get minutes, you'll get the same answer, and the values for L and LQ will be exactly the same. So the units don't matter as long as you keep the same unit. As long as lambda and mu are both customers per hour or both customers per minute, everything works out to be exactly the same. The only thing is the time units for waiting time will be in hours and may need to be converted into minutes. So this is very similar calculation to the example we did before. P naught is 1 minus lambda over mu. Just plug and chug through these formulas and compute these different statistics. Okay, LQ is going to be slightly different calculation because there's a 2 here that was not there in an MM1 system. So remember to use the right formulas. Remember to use the formula from an MD1 slide because the service time is deterministic, and don't use the formula for an MM1 slide. Okay, and you can compute this example for this car wash. We'll have about 0.81 customers in queue at any given time. The waiting time is 2.33 minutes because the car wash takes 2 minutes as well. The total time spent in the system is 4.33 minutes. Our utilization is 70% or 0.7 probability. Our idle time is 0.3 probability or 30% idle time. So the car wash is idle about 30% of the time. Okay. Now let's go to our most complex model that we're going to do today. That is an MMK system, which is basically just like an MM1 system. The only difference is now you have multiple servers or channels. So now you have K servers or channels. So people come, they all queue up in one line, and that one line is feeding K different servers, workstations, or channels. Okay. Now the formulas do change and they do become a little bit more complicated. The formula for P naught, probability that there are no units in the system, is quite involved. You have sigma, the summation term, which you have to compute that, and then you use P naught to compute the other values. Probability of n units in the system is also a little bit involved, and LQ. If you have P naught, LQ is not too bad, but getting P naught is kind of bad. But once you have LQ and P naught, everything else is easy. L is just LQ plus lambda over mu. WQ is this, W is this, and then probability that an arriving customer has to wait is this, right? So this is kind of takes a while to compute, and I don't want you to waste a lot of time just doing manual computation. So there's 2 ways I'm going to help you speed this up. One is I'm going to give you a table. I'm going to show you next how to read with an example. So you can look up the value of P naught from a table based on the value of lambda and mu and K that you have, or you can get to that value based on this Excel file that I'm going to share with you on Canvas. Okay, so here is the table I mentioned. You compute the ratio lambda over mu, you go to that row and you pick the column based on the number of servers you have, 2, 3, 4, or 5 servers, and the value in the table is a P naught value. And so you just read P naught from the table, and then you can plug P naught into LQ to compute LQ, and then you are golden from then on. I've also built in the P naught calculation into this Excel worksheet, so you can put in the value of lambda, the value of mu, the value of K, how many servers you have, and this cell will compute P naught for you. This is the equals compute P naught function that I've written using Visual Basic inside this Excel file, and so you can call the compute P naught function anywhere in this Excel file. Give them lambda as the first argument, mu as the second argument, K as the third argument. It'll give you a value of P naught. Notice the value of P naught is the same as the table. So let me show you an example. Let's say lambda over mu equals 1. So lambda and mu are equal, and you have 3 servers. So lambda is 8, mu is 8, and you have 3 servers. Your P naught should be 0.3636. And if you go here, the ratio lambda over mu is 1 right here, and K equals 3. You get 0.3636. So both give you the same answer. Okay, so you can use this Excel sheet to quickly compute P naught. From P naught you compute LQ, and then you compute the rest. So let's look at an example. This is the same table that's in the Excel file. I've also put it in the PowerPoint slides. You can look up that table here. So you need to know the ratio lambda over mu. You need to know K. K chooses the column, lambda over mu chooses the row, and you just read the value of P naught from the table. Okay, so we have a warehouse. We have 4 unloading bays. These are our channels or servers. We have arrival rate lambda of 3 per hour. Our service rate for each of the bays is 1 truck per hour, so 1 per hour. So mu is 1, lambda is 3, and we have 4 servers. Okay, so lambda is 3 trucks per hour, mu is 1 truck per hour, K is 4. So first of all, step 1, we calculate the ratio lambda over mu. This is 3. And then we know K is 4, so we can find P naught from the table. So we go to this table, we go to a ratio of 3 right here. Then we go across to K equals 4 column, and P naught is 0.0377 from the table. So we go back and we got our P naught as 0.0377. We can also use the Excel file that we had. So we know that lambda, the arrivals are 3 trucks per hour. We can serve 1 truck per hour, and we have 4 serving channels or bays, and so we get P naught 0.0377. The same thing we got from the table. Once we have P naught, step 2, we're going to find LQ, the length of the queue, because once we have P naught and LQ, then finding all the other values becomes really easy for an MMK system. So LQ is this formula. You take the ratio lambda over mu, which was 3, raised to the power of K, which is number of channels, which is 4. So that's 3 raised to power 4, multiplied by lambda, multiplied by mu, multiplied by 3, multiplied by 1. That's your numerator here. Then you divide that by K minus 1 factorial. K is the number of channels, which was 4. So that'll be 4 minus 1 or 3 factorial. Again, factorial just means you take that integer, you multiply it by all the smaller integers. So 3 factorial will be 3 times 2 times 1, which is 6. So 4 minus 1 factorial will become 3 factorial, which is 6. In Excel, you can use the equals FACT fact function. So say equals FACT, in brackets you give it 3, and it will give you the factorial of 3. Okay, then you multiply that factorial answer of 6 by K times mu, which is 4 times 1 minus lambda minus 3 squared. That's going to be 4 minus 3 or 1 squared. So the whole denominator will become 6. The numerator 3 times 4 times 3 times 1 becomes 243. And then you do 243 over 6. You have to multiply by P naught. This P naught right here, which is 0.0377. So when you do the whole computation, you get 1.527. Then we can calculate the total time spent in the system by the truck, which is time spent being waiting, WQ, plus 1 over mu. WQ is just LQ over lambda. So we just get LQ over lambda is WQ. How? We know that from this slide. WQ is LQ over lambda. And so you can replace WQ by LQ over lambda here, and then add 1 over mu to get W. So we do that to find W. So 1.509 hours is what a truck spends at the warehouse, either waiting, about half an hour waiting, and then 1 hour being offloaded. Okay. Now we had some cost data in the question that each crew costs $30 per hour, and the cost of an idle truck is $50 because you have to pay the truck driver the salary even though they're idle, and then the truck is also not hauling any material, so you're losing some revenue because the truck is not transporting anything at that time, so you have some opportunity cost there. So we can figure out the cost of the cost to provide the service and the waiting cost here. Because we have 4 docks, the cost to provide this offloading service is easy to compute per hour. It's $30 per hour to run 1 crew on 1 dock, times 4 docks. That gives us $120 per hour to run this operation. And then we have a waiting cost, which is the cost of trucks being idle. That's $50 per hour per truck. And for any given hour, we have L trucks in the system, right? And we can find L. L is given by LQ plus lambda over mu, right? And we computed LQ as 1.527, so we can do plus lambda over mu to find L. And we can do that L times 50 to get the cost. Another way we can think about it is this way, that we have lambda trucks arrive in 1 hour. Each of these trucks is going to spend W hours in the system. So for each hour of the day, we have lambda times W our truck hours kind of wasted or spent offloading. And so each of those hours costs us $50. So 50 times lambda times W will be the cost of waiting for per hour, because each hour we'll get 3 trucks will arrive. Each of these trucks will spend 1.5 hours in the system. So $26 is our cost, waiting cost per hour. If you don't like the lambda W, just do it with L. It's give you the same answer. You can just compute L and then multiply 50 by L. L is the number of trucks in the system. 50 is the hourly cost of the trucks. Okay. And so then we can find the total cost per hour is the cost to provide the service plus the waiting cost. Okay, that's $346.34 per hour. Now, why did we do all this cost analysis? Why do we find the total cost per hour of the system? That has to do with this picture here. As you increase the number of crews or number of channels and servers you have, your service cost goes up, right? But you also are able to run through the trucks or the customers much faster. They don't have to wait much, so waiting cost goes down. So waiting cost goes down with more servers, but the cost to provide the service goes up with more servers. So there's an optimal point. So for different values of K, you can calculate your total cost and then pick how many servers you should have based on the lowest total cost. So that's why we did all this cost calculation. Okay. Now let's look at the assumptions of all these calculations that we have done. The assumptions for an MM1 system are that customers arrive according to the Poisson distribution, service times have a negative exponential distribution, and then the service rate, the amount, our capacity, the number of customers we can serve per hour or per minute has to be more than the arrival rate. They can't even be equal for these formulas to work. The formulas only work if mu is bigger than lambda. Okay. Then we also assume the customers are served FIFO, first in, first out. Then we have these other two assumptions as well, which are generally satisfied in practice, so we don't have to worry about them too much. One is there's not a limit on length of the waiting line. So the waiting line can be 5, 10, 15 people. Like we're not going to run out of space. If you do run out of space and then no new customer can arrive, then that can, on the margins, affect the statistics. How your system will behave will not be reflected accurately by the statistics. But usually for most businesses, it's rare that you have not enough space for people to stand, although it can happen like on Black Friday where the queue goes outside. But again, that's fine because people can sit outside. That's totally fine as long as there's space for them to stand. And so this assumption is usually not violated because people just queue outside. And the population from which the customers arrive is much larger than the people in the system. So if you have 20 people in your store, your serving population, the area you serve, has a population of a lot more than 20 people. Right? That's usually satisfied as well. For an MMK system, there's an additional requirement that all servers are identical. We are assuming that if you have 2, 3, 4, 5 servers, all of them operate at the same rate. If they don't operate at the same rate, you can just use the average service rate. So on average, you can serve 5 customers per hour at a server or channel, and your calculations will be correct on average. So this is also not a really difficult assumption to satisfy. It's usually just use the average service rate. This one is important. The combined service rate, K times mu, has to be bigger than lambda. So the total service capacity, if one server does 5 customers per hour, the second one does 5 customers per hour, the total of 10 has to be more than the arrival rate. This is very similar to the assumption that mu has to be bigger than lambda for MM1 system. For MMK system, it just becomes K times mu has to be bigger than lambda. And this assumption is really important, that the arrivals wait in a single line before proceeding to the next available channel. If you have a different line in front of each channel, then you have multiple MM1 systems. Multiple MM1 systems is not the same as an MMK system. Okay. For that, remember this picture I showed you. Right here, the picture A is an MMK system. It's MM5 because you have 5 servers. It's an MMK system. The picture on the right, which is picture B, this is not an MM5 system. This is an MM1 system and another MM1 system and another MM1 system. So you'll have to analyze the picture on the right, the picture B, as an MM1 system and then multiple of those. And the picture on the left will be an MM5 system. So you have to make sure that there's one queue feeding all the channels, all the servers. Okay, these are the assumptions to do that. Now we can use these formulas to do what is called service system design, which is a very important idea. We can use these formulas to actually design service systems. What do we mean by design? We can figure out how many servers to have. What should be K, for example. Okay. So let's look at an example. It's a very similar trucking example that we had before. Trucks arrive at a warehouse at a rate of 15 per hour during business hours. Crews can unload trucks at the rate of 5 trucks per hour. Assume Poisson arrivals and exponential service time. So we have the MM, and because we can have more than one crew, we have the K. So it's an MMK system. A crew and a dock cost $100 per hour. So if you have one dock and crew, it's going to be $100. If you have 2 crews working at 2 docks, it's going to be $200 per hour, and so forth. A truck and driver cost $120 per hour, because you have to pay the driver the salary even though they're waiting for the truck to be offloaded or waiting in line. And also the truck is not moving any stuff, so there could be an opportunity cost of lost revenue. So there's a cost of the truck and the driver waiting in line or being served. And what is the optimal number of crews to have, i.e. what is the optimal K value? Okay, so if we look at the ratio lambda over mu, that's 3. So if we go to this table that we have, for a ratio of 3, it's not possible to have only 2 servers. Why? Because K times mu has to be bigger than lambda. So if you have 2 servers, 2 times mu is 10. 10 is not bigger than 15. If you have 3 servers, 3 times 5 is 15. 15 is not bigger than 15. So the minimum number of servers you can have with an arrival rate of 15 and a mu of 5 is 4 servers. Otherwise, your line will grow too long. The queue will blow up. So you have to have at least 4 servers. So that is why you can see that the first number we have for P naught is for a column of K equals 4. Okay, so you can have 4 or more servers. So if you have a K equals 4, you can look up P naught from the table. You can find LQ, and once you have LQ, you can find L. L is going to be 4.527 trucks in the system. So if we have K equals 4 crews, our crew cost is $100 per crew times 4 is $400. Our waiting cost is $120 per truck per hour times number of trucks in the system at any given time, L, which is going to give us $543.22. So our total cost, crew cost, or the cost to serve, this is called the service cost, the cost to serve customers, plus the waiting cost is equal to $943.22. Okay. Then we can repeat this analysis for K equals 5, for K equals 6. Well, you might say, well, I can get K equals 5 from here from the table, but I cannot get K equals 6. There's no column in the table. You can get it from here. You're going to put lambda equals 15, mu equals 5. You're going to put K equals 6, and you can get P naught for K equals 6. Right? And then you can still compute LQ and then L for K equals 6. So I did all this computation for this problem. For K equals 4, we get L is 4.528. The waiting cost is 543. The service cost is 400. The total cost is 943. When you go up to 5 servers, your length of the queue falls because you have 5 servers, they can handle more customers, so the shorter queues, and your waiting cost goes down from 543 to 402. But because the 5th extra server that you just hired, you have to pay them salary and stuff, your service cost goes up to 500, and your total cost comes to $902. When you go to 6 servers, your waiting cost falls even more to $371, but your service cost goes up to $600, and your total cost is higher, and same with 7 servers. So if we plot the total cost with the number of servers, we see that the minimum total cost, which is the cost to serve plus the waiting cost, the minimum total cost is with K equals 5 servers. So using this waiting line analysis for MMK system, you can find the total cost for different values of K and then pick the value of K, which gives you the lowest total cost. Okay. In practice, you may go with 5 or maybe even 6 servers. Why would you pick the number of servers which does not give you the lowest total cost but gives you a higher cost? You might say, I'm going to compete with my competitors based on a higher service level. I'm going to serve and treat my customers better. I'm going to make them wait less. So even though it's going to cost me a little bit more, I'm going to pay that extra amount to try to differentiate myself from competitors. So that could be a strategic decision to have more servers than is optimal, because based on your strategy, you may be trying to advertise yourself as a no waiting type of business or very little waiting. The second service design question that we can answer with this sort of analysis is how much space to have for people to wait. Because if you are a retail store, you have to figure out how much space to allocate for the waiting area. Because if you have too big of a waiting area, then you have less space left over in the store to stock product. And if you use the entire store to stock product, then you have no place where people can queue up before the cashiers. Okay, so for an MMK system, what is the maximum length of the queue? And then the maximum length of the queue will tell me how much space I need, because if my queue is going to be at most 15 people, I know I need to have space for 15 people to stand with their carts and so forth, right? Now, the maximum length of the queue is actually infinite theoretically, because, you know, your entire population, all the people that the Best Buy serves, all of them can decide on the same time, the same day to show up. It's close to impossible, but it is theoretically possible, right? And so your queue, no matter how big an area you have, you could run out of space potentially. But usually we say, okay, we don't want to go with this theoretical possibility because it's very, very remote possibility. We want to find the maximum queue length, which is sufficient for 95% of the time, or 98% of the time, or 99% of the time. So you pick some threshold and you say, what is the maximum queue length that will be, you know, that will hold that maximum, that 98% of the time or 99% of the time my queue will be less than equal to this maximum value. Okay, so once you pick that, let's say you pick 99%, you convert the percentage to a probability by dividing it by 100, so 99% becomes 0.99 probability. Then you compute this value called K. K equals 1 minus the probability, like 0.99, divided by length of the queue for your MMK system. This is not the K in MMK, that's a small k, this is a capital K, this is a different quantity K. So you can find the LQ from the MMK formulas multiplied by 1 minus rho, where rho is the utilization. For MMK systems, rho equals lambda over K times mu. Once you find K, then the maximum length of the queue is given by the simple formula, which is log of K, capital K, divided by the log of the utilization, right? So let's do an example. So it makes sense, right? So, you know, this looks kind of a little bit complicated. Let's do an example. What is the maximum length of the queue 98% of the time? So 98% of the time the queue will be of this length or shorter, with the arrival rate being 8 per hour and the service rate being 5 per hour, and K equals 2. Okay, so 5 times 2, K times mu is bigger than lambda, so we are fine there. If we can find the utilization is lambda over K mu, which is 0.8 or 80%. We can find P naught from our Excel file, right? We put lambda equals 8, okay, mu equals 5, and we have 2 servers, and we can find P naught, 0.111, that's P naught, and we can compute LQ using the formulas we've already seen, right? So LQ is given by this MMK formula right here. LQ is right here. We already have P naught, so we do this calculation, right? So we do this calculation and we find LQ equals 2.844. Then we can find the capital K, which is 1 minus the probability, which is 0.98, 98%, divided by LQ of 2.844 times 1 minus the utilization. And we get 0.035. Then the maximum length of the queue is going to be the log of 0.035 divided by the log of 0.8, and we get 15.004. Okay, so the L max is 15, which means for this MMK system, 98% of the time, the queue length will be 15 or less. So if you have space to hold 15 people, you're going to be good, because it's very rare you're going to have more than 15 people in your store queued up. Okay, so that's a really important analysis, right? Because it helps you design your retail store or your service operation, your facility, your DMV station, or whatever office building you have where you serve customers or people, or a factory floor, right? You may have a workstation which processes parts, and you want to know how many parts can be in the queue in the work in process inventory at a time, because you need to have racking to store them or something like that, right? So you can do this analysis. Okay. The last thing before we end the lecture, we're going to talk about this system, which is the MMK system, you have one queue serving leading into K channels versus having multiple MM1 systems, where each system is an MM1 system, one queue, one server, one queue, one server. Okay, which one is better? Okay, so we are a Kroger store manager. We have usually 4 checkout counters open at any time. So K is 4. We are considering, should we have one queue where people line up this one snaky queue, and then the person at the front of the queue goes to one of the 4 cashiers, or should we have 4 queues, one queue per cashiers? Customers arrive to the checkout area at the rate of 40 customers per hour. The checkout service time is on average 5 minutes, so the cashier spends 5 minutes on average with a customer. Assume arrivals are Poisson and the service times are exponential, so it's MM, and then we have 4 servers, MMK, or we are going to have 4 MM1 systems. So compare the 2 systems on the waiting times and the length of the queue. Okay. So we can do the MM4 calculation. So we can do the calculation. Lambda 1 is 40 customers per hour. That's the first system, MMK system. And then mu, because we know we spend 5 minutes per customers, how many customers can we serve in 1 hour? That's 60 over 5 equals 12 customers per hour. So mu is 12, lambda is 40, K equals 4. So using MM4 with lambda of 40, mu of 12, and K of 4, we can use all these MMK formulas to find LQ, WQ, and W. And we can find these statistics, okay, MMK. Now, what about the MM1 systems? What about this picture here, where you have four cashiers, and each cashier has their own queue? Well, if you have 40 customers per hour arriving to these 4 checkout lanes, each cashier will see a load of 40 over 4 or 10 customers per hour, because the 40 customers per hour will be split across 4 cashier lines. So each cashier line will see an incoming rate of 10 customers per hour. So 10 plus 10 plus 10 plus 10, you get 40 per hour coming total to this area. So to analyze the MM1 system, our arrival rate lambda is going to be 10 customers per hour for each of these MM1 systems. Okay, you're going to get 10 customers per hour coming in. So you use lambda of 10 customers per hour, mu of 12 customers per hour. K will just be 1 because you're analyzing this one system, and you can analyze this MM1 system. Okay. So for the MM4 system, your utilization is going to be 83%. Average number of customers in the queue is going to be 3.29. This is the shared queue. And then the average number of customers in the system will be 6.6. The average waiting time is 0.082 hours, which is about 4.9 or about 5 minutes. And the average time spent in the system is about 0.165 hours or about 10 minutes. Okay. If you have 4 MM1 systems, we're going to analyze one of those systems. So each, and because they're identical, the statistics we compute apply to all of them. So each queue, the queue before each of these 4 cashiers is going to have about 4 people on average. The queue plus the person being served is going to be 5 people in this MM1 system. Okay. And then you're going to have an average waiting time of 0.41 hours, which is about 25 minutes. And you're going to spend a total of 30 minutes in the system, waiting 25 minutes, and then 5 minutes being served by the cashier. Now look how different the two are. We have the same number of servers. We just changed the shape of the queue from being one queue serving 4 servers to 4 different queues. And look at the waiting time. Instead of waiting 5 minutes, people are having to wait 25 minutes. Instead of spending 10 minutes in the system, people are spending 3 times as much, or 30 minutes in the system. Why is that? Now, the video I told you to see in the beginning of the lecture explains very well why this happens. So you can go back and watch why the other lines move faster. This video explains that. The professor who made this video also ran an experiment in the university store in the holiday season to compare one queue serving 3 cashiers in that store versus 3 queues serving feeding 3 cashiers. And the experiment showed, you can read this article, the WSJ article, which is linked at the notes of the slides for details. And the experiment shows that there was a 3x improvement in reducing the time people spend in the system if you have one queue feeding multiple servers. So this system is so much more superior. Okay, so this wins hands down. Right. Now, notice what happens if this customer is taking too long. Maybe they have a bunch of pennies to pay with, or they have coupons, they do price comparisons and price match and all of this stuff. If this customer is taking a long time, it's going to delay all of these 3 customers. They're all going to be, it's going to increase the waiting time here. Okay. So you block the whole line because of this one customer. Let's imagine in this system, this one customer takes a long time. Okay. The line can still continue to be served by the other servers, and the line will continue to move, albeit at a little bit slower pace, because now the line is basically moving because of these servers, and this server is stuck with this customer, but still the line will keep moving. So here, because of this one customer that was taking a long time, you were blocking 3 customers totally. Here you don't block anybody. These customers still keep flowing to different servers. The other reason why this the single queue system is better, okay, is because think about what happens with the server utilization. Let's say this server right here runs through these 3 guys quickly. Okay, unless sometimes there are separations here. So unless these other queues readjust and people switch queues, which again is risky because you don't know if the queue you switch to will be slow or fast. Unless people switch queues, this guy is going to sit idle. Once they've cleared out their 3 customers, they just sit idle. Right, and the other guys other servers continue to work on their queues. So over here, if this server is done with their customers, the next customer just go to them. So nobody gets to sit idle. So there's a higher, there's less wastage of server capacity because which can happen here if one server runs out of their queue while other servers are still busy. Okay. So that doesn't happen here. So this system is better. And if you look at our calculation, the total time you spend in the system is, 1/3 of the time you spend with multiple, MM1 systems, but the same total number of servers. You have, 4 servers in one MM4 system here, and here you have 4 MM1 systems, right? And so it's really surprising. Sometimes people say, oh, it should be the same. We have 4 servers. There should be no difference. But our calculation shows there is a difference, simulation shows there is a difference, and real life experiments show there is a big difference. Now, is the difference really going to be 3x for the time spent in the system? Not necessarily. In practice, if people switch lanes and smartly pick lanes, because this assumes people pick a lane randomly, right? So when somebody arrives here, okay, when somebody arrives, right, in real life, mostly when people arrive, they're gonna go pick this lane, and this lane they're gonna pick the shorter queues, right? They're not gonna go stand here because it's like a longer queue. This analysis assumes that customers pick a lane randomly. So in real life, it's maybe less than 30 minutes, not too much less, still going to be more than 10 minutes for sure, but maybe a little bit less than 30 minutes because people will save some time by picking the lane smartly instead of randomly. Okay. And the other reason in real life you get the total time maybe less than 30 minutes, and maybe a little bit better than what the calculation is showing, is that people might switch lanes. So let's say here another customer gets knocked out and this lane has just one person. This guy might decide, oh, I have 2 people in front of me. Here there's just 1 person. I'm going to move here. Okay, and so lane switching behavior might also, help multiple MM1 systems perform a little bit better than an equivalent MMK system. Not better, but a little bit less worse than the calculations show. Okay, but there is going to be a drastic improvement with going to an MMK system with just one queue feeding the multiple servers. Now, why doesn't that happen? It has to be psychology. We're going to talk about psychology of waiting next, because in an MMK system, sometimes people see this snaky line and they say, oh, even though the line is moving really fast compared to the lines here, the line moves faster, people can sometimes get worried. And if you go to a check-in counter at the airport, they have this sort of a system where you have one snaky type of queue and you have multiple servers here. Why? Because they know that's going to cut down on your total wait time, that you total time you spend in this check-in system. But sometimes this long snaky line can feel kind of, you get anxious. Or am I going to make my my flight on time? Because I have this one long snaky line to check in, then I have to go to this another long snaky line for the security, right? But this line does work better than multiple MM1 systems with their own lines. Okay, but psychologically, sometimes this can feel like a very long line. Even though it's moving faster, we don't process the speed of the line as much. So sometimes people like to do this. Also, the other reason some stores will not do this one, because the long snaky line, if you're standing here and this customer gets done, there has to be some display here telling you, go to cashier number 6 or whatever, right? So you have to set up that display. And some stores do that. I've seen that in TJ Maxx or something like that. There's a store like that in Flint. I've seen that system where they have a display and says, go to cashier this, and they have a line like this. So they are using the superior system in that store. Okay, so let's talk about psychology of waiting. As a manager, you not only have to design a system, do your calculations, compute statistics, and see how much waiting space you need, how many servers you need, but you also have to do things to make the waiting more pleasant for people and understand the psychology of waiting. So here are some rules, some studies that have been research that has been done on waiting. If you want, you can look at the links given in the notes in the slides to access more details about what I have summarized on these two slides. Okay, so number one, unoccupied time feels longer than occupied time, which is why businesses will put TVs, magazines in waiting rooms. You'll have mirrors in elevators because people tend to look at themselves. Am I looking nice? Is my shirt buttoned up? Or look at other people, how they're dressed up, and that helps them pass the time. I didn't know that was a thing. I never do that, but apparently people do that. Research shows mirrors in elevators make the wait a little bit, people feel the elevator, they didn't have to spend as much time in the elevator if there are mirrors. If there are no mirrors, they get bored and they feel the time was longer than it is. People want to get started. So if you do some initial operation with them and then they wait, they are happier than if you make them wait and then do all the operation together. So that's why restaurants will give you menus while you're waiting in the line, or at a doctor's clinic, they'll put you in a room where a nurse will take your vitals, and then you still wait half an hour for the doctor. But if the nurse hadn't taken your vitals and you were not in that room, you were out there in the waiting room, that half an hour would seem longer to you. So when you get started, people are more willing to wait because they feel they're in the system, they're being processed on, or something like that. People have a tolerance for waiting that is proportional to the complexity, value, and quantity of the service they anticipate. So if you only bought one bottle of milk and you're standing in a queue at Kroger with people in front of you with carts stacked up with stuff, you're gonna feel horrible. I just have this one milk bottle, let me get out of here, right? But if you bought a lot of stuff, you're more willing to wait in the queue. So that is why some stores will have express lanes. If you bought less than 10 items or less than 8 items, you go to the express lane because they know that these customers with a few items are not going to be happy waiting behind customers with lots of items. Okay. When you call up the customer service line, sometimes if they know based on past history that this customer had a complex issue, going to take a long time and hold up the call, they might route you to a more experienced service staff who might be able to serve you faster than to route you to a newly hired customer service staff who may take a long time with your complex request, right? People willing to wait longer for a doctor than a checkout clerk because they value the service they get from a doctor more than a cashier checking them out, for example. Uncertain and unexplained waits seem longer than known and explained waits. That is why a lot of times companies will give you the estimated wait time. So you order a pizza from your phone and they tell you pizza will be ready approximately by this time. Or some companies will give you a delivery guarantee. You'll get your product in this many days. So you don't have an uncertain and unexplained waiting experience. Okay. If there's a weather problem, airlines will explain that what caused the delay so that you are not waiting 2 hours, not knowing what's happening, and they might hand out snacks and things like that. So all of this management is based on the psychology of waiting. Unfair waits seem longer than equitable waits. So if you have a first in, first out queue, people know that the system is fair, or you get like a tag with a number and then they call you by the number. So like in a social security office, you get that number, right? So that seems to be a fair system. So people are more willing to wait. Now, if you've been on a subway in a city like Chicago or Toronto on a busy evening, and you know you're waiting for the next train to arrive, and there's more people there, then there might be room in the train, especially at in the morning at the rush hour. People can get anxious. They're like, I may have come first, but somebody else may get on the train before me. Why? Because there's no way to make a FIFO queue on the train station. So that causes anxiety and makes the wait unpleasant, and people don't like waiting without a FIFO system because they feel it's an unfair system where somebody can push through and get ahead faster. And so setting up a nice FIFO queue with barriers or something can also help reduce people's anxiety because they know they are going to be served in the right order in a fair manner. Shorter queues can also make the wait seem less longer. So sometimes you have multiple queues rather than one long snaky queue, even though the snaky long queue will move faster. So to summarize what we did today, we learned how to analyze an MM1 system, an MMK system, and an MD1 system. So 3 types of system we learned to analyze. We also learned about service system design. We found finding the optimal number of servers to use that minimizes total cost, which is waiting cost plus service cost. And we also found a way how to compute the maximum queue length that will not be exceeded for some threshold, e.g., for example, 95% of the time or 98% of the time. And we can use these sorts of calculations to design our service operations. That is all.